let us discuss carding section today. So, the carding section consists of cylinder, a chain of flats, carding bars, front and back plates, doffer, undercasing and suction system. Now, we can see the cylinder and the associated parts around the cylinder, that the cylinder is actually enclosed from all sides, and therefore, whenever the cylinder rotates, the air which is surrounding the cylinder also rotates along with it. Now, we go to the next slide. A cylinder is basically a cast iron shell machined internally at both ends to accommodate the cast iron spider with spokes and hubs. You see the picture and see that the cylinder is supported on a main shaft. The shaft is here is the shaft, and it rests on a roller bearing on pedestal bracket. So, these are the pedestal bracket, here is the roller bearing, this side also we have roller bearing. The sides are covered by metal sheet. So, these are the metal sheets which is covering the sides of the cylinder. Cylinder has a typical diameter which varies between 1280 to 1300 millimeter, and this is the diameter of the cylinder. This is a cross sectional view, what we can see it here, and which is roughly the diameter turns out to be around 53/4 inch, but it may vary from manufacturer to manufacturer to some extent. The length is around 1000 millimeter or little bit more than that. The speed of the cylinder could be around 200 to 600 rpm, depending upon the type of fiber that we are going to process, we adjust the speed, but the flexibility is there and the speed can be maintained between 200 to 600 rpm. The concentricity of the cylinder is very important, and it must be maintained within extreme narrow limits. That is why manufacturing part of a cylinder is not easy from the mechanical engineering point of view. The entire cylinder surface is covered with large number of fine needles or pins. That is all about the construction part of the cylinder. Now, we go to the next slide, where we see how the various parts associated with the cylinders are located around the periphery of the cylinder, and this is what is known as geometry of the carding zone. So, you can see that the chain, this carding machine or the cylinder is actually surrounded by chain of flats, by carding bars, by front and back plates, by doffer on this side. This side we have doffer, this side we have Likarin, there is undercasing at the bottom, and there are suction systems. Locations are here, here, here and here. So, it is enclosed from all sides. Total peripheral length which is available around a cylinder could be around 405 centimeter. This is pi into diameter of the cylinder, and the carding zone which we see it here, it is around 158 centimeter. So, the angles corresponding to different zones are also shown in the diagram. We can see that the angle corresponding to the Likarin zone is alpha 1, then pre-carding zone is alpha 2, then carding zone is alpha 3, then the front or post carding zone is around alpha 4, the doffer interactive zone is around alpha 5, and the undercasing is around beta. Therefore, if I add all these alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and beta, this is going to be 360 degree. Now, the peripheral length is basically fixed and decided by the diameter of the cylinder, and the locations of the Likarin, Doffer, if we change, we can vary the angles alpha 1, alpha 2, alpha 3, alpha 5 and beta. So, the overall peripheral length is fixed depending upon how much zonal length we required in order to ensure that the carding takes place quite efficiently. We can decide about the angles alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and beta. So, typically the angles corresponds to alpha 3 on a machine could be around 148 or 43 degree, but this will vary from manufacturer to manufacturers. From here we go to the next slide and let us look at the flats. The flats are basically cast iron bar as shown it here, and it has a inverted T shape cross section. The lower surface is smooth and contains wire points. So, these are the wire points that we see here. The flat width typically is 32 mm. From here to there, this length is 32 and the wire points are spread over 22 millimeter. So, these are the individual wire points on the flat surface. It is a long bar, the cross sectional view is shown here, and these wire points is spread over a length of around 22 mm. There are number of flats, the total number of flats is roughly from around 80 to 110, which also varies from manufacturer to manufacturer, but it could lie somewhere between 80 to 110. They are all linked together by a chain, and the flat rest on a metallic strip known as flexible band. So, here is the flexible band. The flats will be actually resting on the flexible band, and the flexible band in turn rests on the side frame of the machine. The curvature of the flexible band and the curvature of the cylinder almost match each other. From here we go to the next slide and we see that how the flat ends are supported. There are two types of supports which are possible. One is flat ends are supported at both the ends of the flat. Is basically flat is a long bar T shaped cross sections, and the two ends of the flat rest on the flexible band, and there the here it is being shown how it is resting on the flexible band. This type of arrangement is known as single point support of the flat, that is the contact area is only here over a narrow zone or almost at a single point, whereas in this case, in the other case what you see it here, it is a 2 point support, that is there is a support here and there is support there. Now, this 2 point supports are superior in comparison to the single point support, because when the flats start moving over the flexible band, then the movement becomes smooth if the two ends, these two ends of the flats have a support over the flexible band. So, this is the flexible band. In a single point support, if it is there, as the flats are dragged over the flexible band, there is a chance they start rocking, and therefore, the flats may move up and down, and this kind of movement will actually affect the setting between the flat wire points and the cylinder wire points, and therefore, it can affect the opening action of the fibers between the cylinder and flat. The other important thing about the flat is heel and toe arrangement. Now, what is heel and toe arrangement? The diagram is shown here. Now, what you see, if you look at this arrangement of the flat OR points and the cylinder OR points, then you will see that the way they have been placed, that the narrow gap that exists between the OR points of flat and cylinder, and this gap is converging, that is, it is little more at the entry side and less on the exit side. This is how the flats have been designed. The idea is that it will facilitate gradual increase in the intensity of the opening actions of the tufts. So, as soon as the tuft, which is here, let us say, enters this space, initially there is a large gap between the two OR points, it will enter this gap and gradually it will be opened out. If the gap remains constant throughout, then there is a sudden impact on the tuft and the fibers may break. Therefore, we need to make sure that the gap that exists between the OR points of the flat and the cylinder, for each and every flat, it is large at the entry point of the tuft, and as it moves out of this one single flat zone, then this is little less, and therefore, the fibers are going to receive mild opening actions and chances of breakage will reduce. The other important things about flat is the flats may be considered as a beam supported at 2 points at their ends. So, here we see it, this is the flat, this is the flexible band, and here the cylinder is there. So, this is our cylinder. And the OR points of the flats and the OR points of cylinder, you can see there is a small gap between them. So, the flat, the two ends of the flats are supported on two flexible bends, this bend number 1 and let us say this is bend number 2. The gap between the flat and the cylinder must remains constant, and this gap from one end of the machine to the other end for a particular flat should remains constant. Now, what happens if the bending rigidity of the flat is not enough, then the flat rod may bend like this, shown in this diagram, and if it bends, then this gap that exists between the cylinder and the flat, you see the bending is more at the middle point, and therefore, the gap will be minimum here and the gap at the two ends will be larger. So, the tufts which are here, they will receive less opening action, whereas the tufts which are here at the middle, the gap being less, there will be intensive opening on them, and hence such kind of situations we have to avoid, and therefore, the bending rigidity of the material which is used to make the flats and the cross sectional shape of this flat becomes very important, because we have to ensure that this bending is really minimum. So, this is, and therefore, we go for T shaped cross sections of the flat. From here we go to the next slide. So, what are the function of the flats now? We know this flats and the cylinder OR points, these are the two OR points which participates in carding actions, and therefore, the OR point geometry, the other associated parts of the OR points of both cylinder and flats are extremely important. separations of the fiber tufts including naps to an individual state known as carding action is what is performed by the flats. So, cylinder on its own cannot really open and separate the fiber tufts. Flats on its own also cannot do it. Their interaction between the two wire points actually serves the purpose of separating the fiber tufts into fine individualized fibers, and they can also remove the naps. Second thing what they do, extraction of short fiber, trash particles and dust, that is also performed by the flats, because after carding action part of the fibers are transferred to the flats, and the trash particles which are there, they are thrown by the cylinder because of its centrifugal actions, and the flats surface which is filled up with fibers, they will absorb those trash particles and dust, and therefore, it helps in cleaning action also. Generally both the actions, that is separation of fibers as well as the cleaning part, they takes place simultaneously. However, carding action is completed within first few flats and the cleaning action continues over the entire flat region. We will discuss this point in more detail later, that why do you need so many flats on the cylinder surface, even though the carding action has been shown to be completed within first 10 to 15 flats. So, therefore, the next of the flats basically participate in cleaning the material rather than opening or separating the fibers. Now, a question that comes is that why the flats have to be moved. Flats are given little motion and they move in the forward direction, that is the direction of delivery of the carding machine, they also move. Now, why such little movement is required? The movement is so slow that at times it may appear that the flats are not really moving at all, but if somebody goes near the machine and carefully looks at the flats, then he will find that he or she will find that the flats are moving slowly in the forward directions. The reasons are, the flats would get loaded progressively with fibers and impurities as a result of carding action, and therefore, after some time they will lose their opening capability or carding capability. With a stationary carding surface, if the operation is continued, it will be hindered, since flats have to be taken out from time to time for cleaning. That is, if I do not allow the flats to move, then once the flats get completely loaded with fibers or trash or impurities, then you have to stop the machine, you have to remove the flats, clean them and put them back. So, this is the problem with stationary flats. The oil points of the top carding surface also need to be sharpened from time to time, and therefore, because with time the oil points or the pins on the cylinder and the flats both they get roughened, and therefore, we need to sharpen them from time to time, and for this also we need to move the flats, and actually you will see that we can then sharpen them when the flats are moving. Chain of flats can be driven slowly, which would permit necessary cleaning actions as soon as they move out of the carding zone. So, if we allow the flats to move slowly, then as soon as they move out of the carding zone, we can have a means to clean the flats, or we can remove fibers from the flats and make them available for carding. So, once the flats are cleaned, they may be fed back to the carding zone again, and the flats can participate in carding actions. So, therefore, what we need is movement of the flats. After this, now we will discuss the theory of the carding actions. Now, the classical theory states that a fiber can be carded provided the inclination of the wire points is such that the sliding component of tension acting on the fiber is strong enough to move the fiber down the wires towards its base. This is the condition that we have to meet, and this condition can be fulfilled when cot alpha is greater than mu. This has already been stated earlier, where alpha is the inclination angle of the wire point and mu is the coefficient of friction between fiber and the wire. So, this is the classical theory of the carding, and it talks about the inclination angle of the wire points and which is related to the fiber to metal friction. The classical theory does not take into account the centrifugal force that acts on the fiber, and the second thing is it does not take into account the presence of air current due to the rotating elements of the carding machines. So, from there we go to the next theory, which is known as Strang's theory, which was proposed by Strangs. Here, if we look at this diagram, we find that we have already seen that the cylinder is surrounded from all sides, and as soon as it starts its rotation, then the air that exists between the cylinder surface and the flats, that air also start moving. So, this is the air which is there, this air we can imagine that this air layer will also start moving. The air which is in contact in the cylinder surface, the layer which is in contact with cylinder surface will have a velocity equal to the velocity of the cylinder, and the layer of air which is in contact with the flats will have a velocity almost equal to 0. That means, in this narrow zone the layers are moving at different velocities. The velocity profile of the boundary layer of air is shown in this diagram, which is represented by these arrows. So, the length of the arrows basically indicate the velocity of the boundary layer of air. Now, in this zone we introduce a tuft. A tuft is introduced into this boundary layer, is subjected to a terrific force F caused by the shearing action of the air moving with different velocities in the narrow space between cylinder and flat, and the force which will act on it is represented by this formula F, which is equal to R V A by S, where R indicates the coefficient of viscosity of the air at a given temperature, V is the velocity of the air current, and A is the projected area of the fiber tuft in the direction perpendicular to the air stream, and S is the depth of the boundary layer. And therefore, what happens that the tuft is sheared, because one part of the tuft will be experiencing a higher force and the other part will be experiencing less force. If this is the suppose is the tuft, this part will experience some velocity, the other part will experience less velocity, because the streamline of air are moving at different velocities from bottom of the tuft to the top, and therefore, the tuft is going to be sheared. it will be broken into pieces. So, this theory only talks about the role of air current in shearing action of the tufts. Now, there is another theory proposed by Kaufman, known as Kaufman's theory. In this theory, what is stated is that the air current is not solely responsible for opening the tufts, because even at very low velocity of the cylinder, we have found carding action to occur. That is, as the cylinder speed is reduced, the velocity of the air will also reduce. It has been found that if we bring down the cylinder speed to a very low level, suppose around 10 rpm or maybe 20 rpm, we can still find carding action to take place. Therefore, it was proposed that it is not only the air current that is responsible for opening the fibers or tufts. So, what it is here? The tufts held on cylinder surface approach the cylinder flat zone at a very high speed and are introduced into the narrow gap between the flat and cylinder. So, from this side, here is a tuft. This tuft is coming from this side, because it is sitting on the cylinder, and as soon as it comes near the cylinder flat zone, the lofty tufts is forced into a narrow zone, and as soon as it enters this zone, compressive force will develop on the tuft, which will force the fibers into the oil clothing of both flat and cylinders. Therefore, compressive force will develop on them, and the tuft will get into the oil points of flat and also the oil points of the cylinder. Since flats are practically stationary as compared to the fast moving cylinder surface, the loading factor of compression force against the flat is much more than against the cylinder. A cylinder presents a large surface area for the same compression force. See, practically flats are almost stationary in comparison to the surface speed of the cylinder, and therefore, the same compressive force will act on a larger surface area for cylinder in comparison to flat, and therefore, we can say the loading factor of the flat will be more in comparison to cylinder. The penetration of the teeth into the tuft is immediately followed by shearing actions. Due to great differences in speed between flat and cylinders. So, as soon as the tuft enters the narrow gap, the oil points will be penetrating the tuft. Now, the bottom part of the tuft and the top part of the tuft are moving at two different velocities. V c is the velocity of the cylinder and V f is the velocity of the flat, but the velocity of the cylinder is extremely high in comparison to that of flat, and hence the tuft will be sheared immediately, and the tuft may be sheared somewhere here at the middle or any other locations. The part which remains on the cylinder will move forward and it will be introduced into the subsequent cylinder flat zone, and again the same compression will take place on the flat on the tuft, and the same process will repeat. And this process of compression, penetration followed by shearing will repeat itself as long as the cylinder is carrying the tufts along the carding zone. As a result of this, the same tuft will be diminishing in size, and the big tuft will be subdivided into number of small and small tufts. This is how the opening action is happening in the case of carding action, in the case of carding. So, these are the three different theories proposed. Now, we go to the Licardin and flat region. So, this region is shown in this diagram. This is the place which is called Licardin flat region. This region also is covered by pre-carding segments consisting of mode knife, suction hood and adjustable bracket known as back plate. What is the purpose of this zone? The Licardin is here. From the Licardin, tufts are fed onto the cylinder. Cylinder will carry the flats or these tufts to the flats. Now, the tufts which are laid on the cylinder surface, they are of varying size and they may be distributed non-uniformly on the surface of the cylinder. And therefore, what we need is to give a mild opening treatments to the tufts and to orient them and distribute them evenly on the cylinder surface. That is one of the purpose why we have a carding plate over here. That is, in this zone little space is available, we make use of this space in terms of further opening the tufts before they are introduced into the very narrow gap between cylinder and flat. And therefore, we have the carding plates, the suction hood also, because as soon as opening takes place, there will be always liberation of dust, and we make use of this situation in terms of sucking out part of the dust. Further, because of centrifugal force, lot of fibers may be thrown. Therefore, this zone needs to be covered. We cannot leave it empty, otherwise we lose lot of fibers, and that could be also a chance of accidents. And as soon as they are covered, it can prevent uncontrolled air current which may disturb the arrangement of fibers on the cylinder. So, therefore, this zone is covered and we make use of this zone in terms of cleaning and opening the fiber tufts. The cleaning is required when you process cotton, but when you do not process cotton, then cleaning is not really important, but uniform distribution of the tufts from Licardin onto the cylinder surface is important, and hence we must have some carding bars there, pre-carding bars. The carding bars have a special type of clothing, so that they do not get loaded with fibers, and it does not need cleaning frequently. Otherwise, if they hold too many fibers with them and do not allow the fibers to move out, in that case all these carding bars will lose their opening capability very fast, and it may lead to generation of naps. And hence, the design of the word points over the carding bars is very important. Their word point geometry, the kind of finish which is given to the word points, the angle, the densities, everything is important. This will be discussed in more details in some other lectures. We have discussed the Licardin flat region. We stop today. Thank you very much.